So thank you for being here tonight at our Alliance of International Aromatherapists Research Academy presentation by Bruce Boynton. So Dr. Boynton has had a distinguished career in healthcare research, public health, medical publishing, and medical administration. He's been a professor of pediatrics, a pulmonary physiologist, director of an infectious disease research lab in Cairo, Egypt, commanding officer of the USNS Comfort, a 1,000-bed hospital ship, Deputy Inspector General of U.S. Navy Medicine, and statewide director of a correctional medicine for Mississippi and New Mexico. He's currently the editor of the Journal of Health and Human Experience and is a member of the AIA Board of Directors and a member of the Clinical Research and Research Steering Committees. So there's Bruce. I give you Bruce.
Okay, well, thank you all for being here. And I'm going to share. And that should be coming up. Okay, here we go.
Ooh,
Statistics 101, the good, the bad, and the ugly. I know that math and statistics is not the favored subject of everyone. My sister, when she was in school, almost had a nervous breakdown because she could not figure out what the common denominator was of fractions. So I know this kind of feeling well, but this is going to be easy. So what this presentation is going to be about, it's going to be about statistics, but from a 100,000-foot view. What are the concerns of statistics? I'm going to orient you, give you some vocabulary and grounding statistics, and this is going to be the foundation for more advanced classes. So eventually we'll have some classes on how to do t-tests and analysis of variance and logistic regression and summary statistics and this, that, and the other, non-parametric statistics. But this is first. This is just about the field. And finally, when do you invite a statistician to join a research group? What this is not about is things to memorize, complex formulas, computing significance, how to design a study, or doing anything difficult. Now, statistics is about data. That's what statisticians do. They collect data, they analyze data, they interpret data, and they present data. And they have very decided views about how each of these tasks must be done. So what I'm going to do in this presentation is talk about how statisticians collect, analyze, interpret, and present data. And so those are going to be the four sections of this presentation. How do we collect data? How do we collect data that makes sense, that we can analyze, that we can present? Well, we're going to start out with a thought experiment. What is the best way to find out the opinion of the 10 figures below? What do you think? This is easy. Ask them.
It's all good.
Okay. All right. The claim of statistics. This is a bigger sample. This box is referred to as it is your sample space. These are the people, the many people, the millions of people who you want to draw inferences about. You want to know about those, but you can't you can't interview 1 million people. So what the claim of statistics is, we don't have to interview 1 million people to know their opinions. We can take a sample, and by studying that sample, we can infer the opinions of the people that we don't study. That's a pretty bold claim. If you take the right kind of sample and study the sample, you can infer the opinions of people that you don't sample. And that's, of course, what they do in polls. They ask a certain selected sample, and they tell you whether the race is close or not. Now, this arrow right here is the sample. Is that sample a good sample? I don't know. It's got a lot of dots in it. It's got different colored dots. It might be an okay sample. Here's the trick. The sample must be just like the population you want to study, only smaller. So there we have Austin Powers and Mini-Me, just like that. Okay, here's an example. Let's say you took a huge sample, say 15 million people in your sample, but you took them all from California. And here, these are the results of the election. Harris got 9 million votes. Trump got 6 million. Harris got 58% of the votes. Trump only got 38%. If you sampled only in California, you would draw the wrong conclusion. No matter how many people you sample. The reason why is that California is not like, every state is different. Let's say West Virginia, Harris got 214,000 votes, 28%. Trump got 533,000, 70%. If you just sampled in West Virginia, you would draw the wrong conclusion too. So the sample has to be representative of the group that you want to draw inferences about. It has to be like a mini-me. So what's the problem with a non-representative sample? The problem is that you can know everything about that sample, but you can't extrapolate those results to the larger population of interest. Okay, how do you draw representative samples? Well, the first thing is you look at the web of causation. Diseases and human attributes don't have a single cause. Here's a little web of causation that has to do with heart attacks. Heart disease right here. So it depends on whether you're obese, whether you have hypertension, whether you have heart in the arteries, your cholesterol, your exercise. It depends on a lot of different factors. Some of those factors may be very important in choosing the sample that you study. So sketching out a web of causation usually informs you about all the factors that go into some outcome. This is another example. This has to do with essential oils and migraines. What is the cause of migraines? Well, how do you remove migraines? Well, they have a lot of different things: massage, acupuncture, different herbs, or aromatherapy. If you use aromatherapy, what oils are you going to use? What is the composition of those blends? And then things like that are internal to the physiology, like neurogenic inflammation, central pain sensitization, things like that. Okay, so everything that we look at, let's take anxiety. A lot of different things go into making us anxious. It's what's happening in the 3D world. It's whether we're prone to anxiety. It's whether we've dealt with issues by being anxious in the past. A lot of things. Now, you'll find different kinds of variables. In the example that we used for heart disease, one example would be whether the people have hypertension or not, what their age is, what kind of diet they eat. Do they have hardening of the arteries? Then there's variables that you don't know, but may be important. One of the ways we get rid of different variables among the different groups is by randomization. What does randomization mean? Randomization means ensuring that each and every volunteer for your study has an equal chance of being chosen. For instance, if you decided that gender was an important variable, you wouldn't want to pick all women or all men. You would want to pick equal numbers of each gender. And so here's a sampling problem. You're studying the effects of lavender inhalation on a standardized measure of anxiety. And there's something called GAD-7, which is recognized by psychologists as a good tool to measure anxiety. So you're going to, some people will be in a control group and some people will be in an intervention group. So let's pretend we have 20 people that are going to be in the intervention group. So they're going to inhale lavender, and the 20 that are in the control group are going to inhale, say, sham lavender. And that could be like a scent or a perfume or something like that. Sham lavender is something that doesn't have the physiologic effects of lavender, but will be something that they can sniff. And now, how will you select the experimental subjects? Well, it's really pretty easy to do. You can generate some random numbers, and that's very easy to do. There's all sorts of programs on the web. You can just put in pseudo-random numbers or something in your browser and pull it up, and you just enter the data, and it will, that is, you say, I want a series of random numbers, let's say 20 of them from 1 to 50 or something like that. So now you have the random numbers, and let's say, we'll say even numbers will be in the intervention group and odd numbers will be in the control group. So just lay the numbers out and count 20 even numbers, and those people are going to be in the intervention group, and then the rest will be in the control group. It's easy peasy. All right, here's a little bit harder one. Again, you're studying the effects of lavender inhalation on measure of anxiety. You decide that gender is an important variable affecting the outcome. Again, you're going to have 20 in the experimental group that inhale lavender and 20 in the control group. that inhale something else except lavender. So how will you select this experimental subjects? Well, we want equal numbers of men and women in the experimental group and equal numbers of men and women in the control group. So let's take another series of random numbers, and let's say we're just going to work on the experimental group, the intervention group. We say the even numbers are going to be men and the odd numbers are going to be women, or vice versa. And you just count off 10 even numbers, and they're going to be the men in the inhalation group. And 10 odd numbers, they're going to be the women in the inhalation group. And there you have the inhalation group. And you do the same thing for the control group. So now you have equal numbers of men and women, and you have the all the volunteers split into inhaling lavender or inhaling something else, being in the control group. Okay, data analysis. How do we approach that? This graph is called a histogram. You see a number of bars and then a curve that's made over it. This curve is a theoretical curve. That's what would happen. You would see that if you did an infinite number of subjects. So we can't do an infinite number, so we just do several. And this is a graph of height in inches against frequency. It's not really frequency, it's number of people, because this is 200, 400, 800, 1200. So it looks like, okay, so this is 70 to 71 inches. And this is looks like about 1,200 people or 1,200 males were between 70 and 71 inches tall in this study. And there were slightly more that were between 69 and 70 inches, and even more between 71 and 72 inches. So this is a histogram. These bars are called bins. You can think of them as little narrow silos that they accumulate observations. And the observations are how many people are 71 inches tall or 75 to 76 inches tall. Now, you see there only is one peak of this curve. In fact, this is called the bell-shaped curve, and there's some other names for it too. And there are very few people in the tails. These are the tails. And most of the people are right in the center. Here's a bell-shaped curve, also called the normal distribution. So a lot of statistics is built around this bell-shaped curve. Let's ask some questions of this curve. This is they don't use average here. They use this Greek letter because this is theoretical. But most of the people are right here. That's the most common observation. The center is right here. If you take the mid-range from here to here, that's right there. And more importantly, in a bell-shaped curve, 2/3 of the observations line this green. And if you go from pink to the end of pink, that's 95% of the observations. And if you go from this end of this blue to this blue, that's 99% of the populations. So it works out really neat. And you might think there are a lot of distributions, and I'm going to show you some, but why is this so important? It's because it's easy to figure. And there's another reason too. It's very, very easy to take data, a set of data, and then you can take different samples and calculate the average. But if you take all those averages, they make a bell-shaped curve. Really remarkable. Okay, here's a histogram that has a different shape. This is like logarithmic, so it has a tail way out here. Most of the observations are very low, and it falls in this gentle curve. Here are some different shapes of histograms. Here's the normal or bell-shaped curve right here. It has a single peak. This is said to be right skewed. The example that I just showed was right skewed. How to remember that? You go to the small end and think of someone tugging on this last observation and dragging the curve out. Here's left skewed, so you think of someone here stretching it out. This is a uniform distribution. This is what if you get if you just put random numbers in. Every number has an equal chance of being chosen. They're all equally likely. Now, the bell-shaped curve is unipolar. It's just got one hump. Here's some that have two humps. You see that less often, though. Now let's analyze a simple data set. Here's the data set. These are random numbers. If you look at that, so all the truth, everything that you can find out about this array of numbers is right here, because these are the numbers. But our minds can't grasp this. If you just look at that, you just see numbers. You don't see a population, you don't see a distribution, you don't see which is the most common number, you don't see if it's one hump or two hump, you don't see if it's right or left skewed. We can't figure that out. What's the most common number? Are some numbers more common than others? What's the center point of the number array? What's the spread of the numbers? That's what we're going to tackle next. The first step I usually do with an array of numbers is make a histogram. I can examine the shape of this distribution. I can tell something about it. I can look at its spread. And then further, after my histogram, I'm going to try to figure out what's the center of the distribution. How's the data spread? Is there one peak or more? Okay, how to make a histogram. Here are three easy histogram sites. You just enter the data and it calculates the histogram for you. And this is just three of many, many. Okay, the sample data that we had, this is a histogram. Wow, this is pretty confusing. It should look like a flat top, right? Because these are random numbers and have equal chance of being chosen. But if you have small samples, it looks wonky. If we kept, I only had like 53 observations, but if I had hundreds and hundreds, it would look more flat. Okay, this is another histogram. This is a graph of household income and what percentage of families have that income. See, there's a single peak. It looks like it's skewed to the right. It rises, so there's a few people that have very low incomes, and then it rises, and the middle is around here somewhere. It's not the highest, not the lowest. They've also said this is the beginning right here. This is the top 5% of families. This is the top 10%, and so forth and so on. How would we find the center of the distribution? Well, there are several different calculations that we can do. The one that's most common is called the arithmetic mean, or the average. It's the population average. You just add up all the numbers and divide by the number of numbers, and you get the mean. Very simple. The median is another way to find the center of the distribution, and it's the central number. So what you would do is put all the numbers in order, and you just count down the row until you find the central number, or you can get a computer program to do it for you. The mode is the most common value, and of course the mode and the mean and the median of the bell-shaped curve are all the same. The other is the mid-range, and you take the smallest number plus the largest number and you divide them by 2. That's simple. Okay, here on this histogram we saw before, they've already calculated the median for you. Sometimes the median is the best guess at the population middle, and sometimes the average is, or the mean. There's a little problem in a book that says, can it be that everyone makes less than the average? Yes, you can do that. Here's the example. You have a lot of low-paid workers, and you have the boss who makes $1 billion a year. So everyone is below average, because when you add that billion to the low workers, the low wages of the workers, it comes out to be an average that's greater than their incomes, but less than the bosses. Okay, here's a program that does some sample statistics for you, and these are very easy to find on the web. Gives the minimum and the maximum, the range, which is the maximum minus the minimum, which is 9, and the size, which is 52. And here they figure, okay, here's the arithmetic mean or average, and it's represented by X with a bar over it. It's called X barred. And so the mean of our sample data was 4.9. The median, which you made an X with a tilde, a little wiggly sign over it, is 5. Really pretty close, 4.9 and 5. The mode, the most frequent number, was 3. And then these are measures of spread, which we haven't got to yet. How do we find the spread of a distribution? One way is the range. That is, the range is simply the largest number in the array minus the smallest number. So in our example, remember it was 9. 9 was the highest number, 0 was the lowest number, so 9 minus 0 is 9. The variance and the standard deviation are more complicated, but what they are is the variation. It measures the variation of the observations around their average. So you can think they have a mean, and how far is each point from the mean? That's what variance and standard deviation measure. Okay, here we go. Range, maximum value minus minimum value, 9. Standard deviation, how far are the observations from the arithmetic mean? Okay, and we go back to our program, and it does it for us. Standard deviation, 2.85. The variance, which is the square, is 8. The mid-range is 4.5, and of course the range was 9. data interpretation. So what does it all mean? Okay. The most common statistical tests that you will do are tests to determine whether a set of observations belongs to one group or another group. Now, one of the ways you might think about it, are the experimental group's results the same or different from the control group? That's something that you want to figure out. If they're no different than the control group, then you haven't done anything for the experimental group. An example would be in our inhalation of lavender, did the experimental group which sniffed lavender have less anxiety, the same anxiety, or more anxiety than the control group that sniffed something else? Okay. Another example is you have a bunch of people with a particular symptom or sign. Are these people belong to the well group or the group with some disease or something or other? Okay. The second group of tests that is most commonly done is to find the relationship between two variables. For instance, what is the relationship between anxiety and lavender inhalation? Okay, here's an example of two groups. You know, no one has the same, exactly the same observation, so they're going to fall in a range. Let's say this line here will be a measure of anxiety. And so these are high anxiety folks. And so this is going to be like the control group. Now you have lavender inhalation and you measure their anxiety. And so this is the experimental group. Is this the same or different than the control group? Now it depends a little bit on what people you choose and how they react to lavender. For instance, let's say all your observations for the control group were in this little area right here. Well, there's an overlap of the two curves, so you can't tell. If they're all over here, then it's easy to tell. So nothing is absolutely certain in statistics. Okay, what if we compare two groups of observations? What are the kind of tests that we might do? Let's take the first example. Are the experimental observations different from those of the control group? The most common test to do is the student's t-test, and that's for two groups of observations. So the lavender example would be, yeah, two groups of observations, the control, the experimental. Are they the same or different? If you have more than two groups, three or more groups, then you would use an analysis of variance, which is more complicated. Now, there's a limitation on the analysis of variance. Let's say you have 5 groups and you want to see, are they different? The analysis of variance will tell you that at least one of those groups is different than the other 4. Well, which one? Or are there more than one? So you may have to do some more testing. All right, what about the second example? What is the relationship between two variables? Well, we can use a scatter plot, calculate a regression line, and calculate a correlation coefficient, and I'll explain all that. Okay, just as you could do the summary statistics on the computer, you can enter the data and it'll do scatter plots too. And this is, again, easy to find on the computer. Okay, so I went into one of these programs and I just made up a bunch of values. Now, when we do a scatter plot, each individual is going to have two values, an X value and a Y value. Now, the X value could be, I don't know, how they did on their anxiety test. And the Y value could be, I don't know, their age, their preferences for different aromas, their gender, any numbers of things. Okay, so I'm doing this scatter plot, and here it is. Now, so these are the points that I picked. All right, so this point here has the value 4, it looks like about 7.5. This point here has a value of, say, 5.5 and 10. Okay, and this is the regression line, which is the best fit for these points. And you see it really approximates them pretty closely. So the claim from this scatter plot is as X increases, Y also increases by a specified amount. Okay. Now, when we do tests in statistics, it introduces us to two new hypotheses. Now, we talked about the hypothesis that generated and inspired your study. For instance, when I sniff lavender, I get calm. Maybe that works for everyone. I'm going to do a study with people who are anxious and see whether those who sniff lavender get a decrease in their anxiety more than those who are in the control group. This is not that kind of hypothesis. This is a hypothesis just for doing the statistical test. Now, how do we prove that the control group and the experimental group are different? How do you prove that? Well, that's the purpose of these hypotheses. The null hypothesis, which is H, and then there's a subscript 0, there's no difference. That's very conservative. I'm going to assume that there is no difference between the groups, okay? Now, when I do the test, if this null hypothesis has a very low probability of being true, then I'm going to reject it in favor of the alternative hypothesis. There is a difference. So you prove that there is a difference by showing that the hypothesis that there is no difference is very unlikely. Okay, so let's say, well, let's advance the slide. That has to do with your p-value. And the statistician does not pick the p-value. You, as the experimenter, pick the p-value. A p-value of p less than 0.05 means that the probability is less than 5% that the null hypothesis is true. When we get a probability that low, we will probably reject the null hypothesis in favor of the alternative hypothesis. There really is a difference. Okay, now I'm going to move on to how do we present data. There's a lot of good graphs out there and a lot of bad ones. You start by keeping it simple, stupid, the KISS program. Be honest. The data speaks for itself. You don't have to manipulate it. Make your audience understand your graph or your chart in 10 seconds or less. There's bar graphs, pie graphs, scatter plots, and regression lines. And we're going to show some charts that are bad, some charts that are good, and I'm going to teach you some tricks that people who are dishonest use to present their data. Look at this graph. Can you understand it in 10 seconds? I've looked at it for hours and I'm still not sure what it's about. We have a line, 100% iron, 33% iron, 50% water, 100% water. Then there are these weird things that look like contour lines, which I think come from this lump, this hump, which I don't know what is. And then you have, you had Uranus and Neptune up there. So I still don't know. I think it's about astronomy. That's not a good graph. Here's a scatter plot. You can't make anything of this. They've plotted too many points. Look at this. This is famous authors and their plot elements that are on the right. I mean, it's beautiful in a way, different colors and stuff, but I can't understand it. It would take hours to dig into that to really get any information. What about this? This is COVID deaths. Can you understand that? There are different dates, different spirals, just all sorts of crazy things. Now, here's something that's really straightforward, a graph to show people's favorite day of the week. On the x-axis are the days of the week, and on the y-axis are the number of people. That's really easy to understand. What I don't understand is why Monday and Tuesday are so popular. Okay, now it's your turn. Look, over 100 million people in the U.S. are receiving some form of federal welfare. This has got to be stopped, right? This is done by dishonest people. Can you figure out what the trick is that they used? Anybody? All right, I'll tell you. This goes up to, looks like 108 million. And here is 94 million. So it only goes up 14 million. That is, this graph starts with an origin not at 0, but at 94 million. And it goes up to 188 million. So most of the graph is below the slide. People do this to make a small change look like a big change. They stretch out the top and they cut off, it's called truncating the y-axis. You'll see this all the time. If there's no difference and they have to show a graph, they'll cut off the y-axis and stretch it so that it looks like something it's not. Okay, look at this one. Violent crime is a very big problem. Oh my gosh, what are we doing? What do you think? Is this an honest graph? Well, okay. Once again, they truncate the y-axis. This goes from 35% to 55%. So most of the graph is below the graph, most of the data. The other thing that they do, which is bizarre, is they have the x-axis going backwards from 2018 to 2021. So really, you could argue that compared to this point, violent crime is falling, not rising. You see that? Okay, pie graphs. I'm not a proponent of pie graphs, but some people are. This is a very clear pie graph. It's made even more clear by them putting the percentages up there on the graph. The reason I don't care for pie graphs, although this is a good one, is that it's harder for our eye to quantitate area versus length. We can tell difference in lengths very easily, but area, less clear. Okay, I'll show you some bad pie graphs. Look at this. Yesterday's results. What is the best part of the Super Bowl? Yes or no? Not only that, it doesn't answer the question. They've got the sections of the pie graph labeled wrong. This small section here is 73%, and this big section is 28%. Okay, scatter plots and regression lines. Here's another scatter plot. This is an interesting one. This shows the number of cats you own as a function of years. Now, I know I have a friend who's a cat fancier, and she's about 60, and she has 4 cats. Yep, absolutely. This here, y equals x plus some, this is the equation of the regression line. You don't have to figure it out that. This is interesting. R squared is the square of the multiple correlation coefficient. That's a mouthful. But what you remember about this is that it explains R squared explains the variance this way and this way around the regression line. Okay? So some are very close to the regression line, some are further away, blah, 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 blah. But this equation explains 84% of the variance. That's huge. So age really is a good indicator of the number of cats you're going to have. I don't have any cats at this time. I'm over here somewhere. Okay. Where to find statistics help? Okay, look up colleges or universities in your area that have PhD programs in statistics, and then call and see if you can find any graduate students. This is what they're studying. They're studying not only complex, tests and things like that, but they also have courses where they help people with their data. People just like you. And if they can make a little, most graduate students are poor, and so if they can make a little bit money and help you out, they'll be happy to do that. So statisticians can help you choose a representative sample. If your sample is not representative, you're just out of luck. Help you analyze your data. What does it look like? What's the distribution center? How's it spread? What can we do with this? Draw conclusions by performing statistical tests and present your data. Make honest and compelling charts and graphs. I have one book to recommend to you, How to Lie with Statistics by Daryl Huff. This book is at least 50 years old. It is recommended in almost all introductory statistical courses. Daryl Huff is more a journalist than a statistician. And the stuff he says he covers everything. is very easy to understand, and much of it is funny. As an example, he has headlines by people who don't know any statistics. For instance, the seminal headline in the San Diego Union, which was tests show that 50% of our students are below the median. Shocking. That's the definition of median. 50% of presidents are below the median. 50% of geniuses are below the median. Whatever, because it's just the middle. Okay, references. There's lots and lots of stuff. I think the best thing is probably you can take these off, and they work well and they're easy to do, but is to find the program that really works best for you. Questions?
Can you hear me?
Yes.
Okay, this is Amy.
Yeah.
So if I'm a grad student in studying nutrition, and I'm going to probably be doing a survey with people who are volunteer out of Facebook social media support groups for those with mast cell activation syndrome. And this is where, you know, what you described is something where you have a control and you have then your test group.
Right.
But with a survey, you don't have that, but you still have to generate stats. So I don't do math very well. And so I'm just trying to figure out, how do I go about thinking about statistics with respect to a survey type?
Right. A survey is the easiest study to do, because you only have one group. And I think that the statistics that you will probably be generating are just summary statistics. Things like the average person did this, 10% of the people did not do this, or whatever. That's going to be very easy.
Super straightforward then.
Yeah,
Okay.
yeah. And you're going to start out again with a you know, it's interesting. One of the things you can do, about how many, do you have any idea how many people you'll be able to survey?
Well, between the three groups on Facebook, it's around 90,000 people, but obviously not that many people are going to participate. So if I had, and they're very active. So if I probably need to cap it at some point, you know, maybe, but I just don't know what would be a statistically sound cap for what I'm asking, because I'm not just looking at an antihistamine diet and a few supplements. I want to know what supplements they've taken that work and that don't work in correlation, and diet in correlation to their specific symptoms.
Right.
So some people like myself, I have mast cell activation syndrome. I get anxiety, insomnia, tinnitus, and tachycardia, like the whole body palpitation stuff. Other people get hives and GI effects. So I want to ask, if the question is like, are there better targeted therapies for specific common, you know, reactions per person for that, or so, you know, let's say 300 people get a spectrum of, or a constellation of the full spectrum of symptoms.
Right.
You know, are they finding relief from targeted therapies? Because no one's actually asked that question. They just go like, okay, well, like luteolin works and quercetin works, but doesn't work for everybody, especially if they have like salicylate issues. You can't take quercetin. So it's just kind of like, you know, what kind of do I need some kind of fancy stats for that, or will I just
I don't think so. I think it's straightforward, but you can do some very, very interesting things. For instance, let's say the people who get hives,
yeah,
segregate them out And if you have a large number, you could look at their distribution and what they get hives from or whatever. And then each of the variables in symptomatology or in cause or anything like that, or just demographics like are men different than women?
Yeah.
Are young people different than old people? Are people who are allergic to many things different than people who seem to have few allergies? So you could really dig into that. I would start with thinking about not only what causes, but what is the range of symptoms,
Yeah.
um, and um, and what is the range of treatments? The people who are on X drug, uh, are they different in any particular way? So there's going to be a lot of exploration, but that's fun.
Yeah. You want to help?
Sure. Just as soon as I finish this presentation.
Yeah. I'm really excited about this, but the
Yeah,
whole like how to, and I think some of it will just be revealed as the data comes in and I start.
exactly. That's the
Yeah.
exciting part. You're learning stuff. You're learning stuff that no one knows before.
Right. Yeah, usually it's just like, oh, try this. Oh, if you can't do that, try that. And there's a lot of interventions where there's evidence base for them, but people aren't even talking about it very much. Just occasionally do I see it pop up.
Yeah,
So
is this going to be for like a thesis or?
this is my dissertation.
Oh,
Yeah.
okay. For like a PhD?
Yeah.
Woo. Okay. Um,
Yeah,
I
I was going to do something with gut microbiome when I started my PhD, and then I got MCAS, and I got it under control, but it was horrible for about a year until I figured out with the help of a functional doc what was going on. And the gaslighting that occurs with people who have MCAS, they're like in anaphylaxis in the ED, and they're being told that it's just all in their head, and they're making, that they're hyperbolic about their symptoms, and they're like, I can't breathe. Like, it's crazy.
oh,
Yeah.
segregate them out too and tell
Yeah.
them this is exciting.
It is exciting. And what I seem to have found from looking at these people making different posts on Facebook, that it's accelerated. The incidence of MCAS is accelerated since COVID. So, and
Oh,
there's a lot of research right now that COVID-19 is a driver for this immune dysregulation
I'll
through
believe that.
kind
Yeah.
of like a cytokine, inflammatory
Yeah,
precursors.
cytokine storm. Yeah.
Yeah, it's just like something's not turning off. And it could have a
Right.
genetic, like an epigenetic component to it where
Mhm.
something's gotten turned
You could
on.
also look at people with who are diagnosed with other things like long COVID.
Yeah.
Are
Long
they
COVID is
different from
highly,
people who
yeah.
had whatever?
There's a lot of overlapping symptom, with between those two.
Yeah.
Yeah.
Cool.
It's super,
Yeah.
super interesting. So
Any
thank you
more
for your
questions?
help.
Anyone else? Anything you didn't understand or you want to make a comment about or something?
So Bruce, this is Marnie.
Yeah.
Hey, so I don't know, I was listening to Amy, but I just wanted to make a comment about research you know, in general. It is what you're passionate about. It's the only
Yes.
way that you're going to be able to slog through what you're going to slog through to do research. So Amy, it sounds like you're really passionate, and you've got a horse in the race too. So you need to be you got to set yourself aside too in the mix of interpreting your data. Like there's bias when we're doing research that we're really, really passionate about. So I'm sure they're talking to you about that in your program and how you can set your biases aside, maybe so that you're getting a balanced look at it as well. And then what comes to mind is something like focus groups might give you a better idea. You have this hypothesis that there's something more. Maybe focus groups at some point would be good. And that's just thoughts about it. Thanks for sharing, Amy, and Bruce, thanks for sharing.
Yeah, I just want to make sure.
I'm sorry.
I just wanted to say, I just want to make sure that if I put like a call for volunteers to these support groups, that the volunteers, it's not going to be like a bias sample. They're just, I don't know who they are. You know, personally, I don't know any of them. And if they just sign up, I kind of want to look at all, like, I don't want to just look at a certain age range or a certain sex or whatever. I think it's across the board. But then there's different genetics for people, you know, I don't know if there would be, I want to just make sure there's no bias. Like I have a good sample size.
Marnie, I really like what you
sample selection, sorry.
Marnie, I really like what you said about basically you have to have a fire in your belly because research is hard. And if you're not interested in it, it's not going to go.
Yeah, but it sounds like Amy's very interested in, I think Amy, more about the bias about analyzing your data and interpreting your data. It's not so much in getting your sample. You're going to get volunteers, you're going to get people you don't know. Just thinking about your analysis of it, your write-up of it. And the other thing, I don't know where you think you're going to publish, but start with the end in mind and take a look at whatever journal you want to publish in. Make sure you've got your things done, your review board and all that kind of stuff. And
oh yeah, I have to go through probably an IRB just to even do that. Yeah.
Right. And just look at journals though, if you want to, go to some journal that just figure out what they want, how they want it written up. And it really helps to start with that in mind from the beginning. Good luck.
Oh, thanks.
Okay, if there are no more questions, I guess we've come to the end.
All right. Yeah,
Thank
I
you,
did
Bruce.
see questions
You're
in
welcome.
the chat. So Bruce, I think you're all set. Thank you so much for presenting tonight. And thank you all for attending.
Absolutely.
Thank you so much.
You're certainly welcome.
I really appreciate it.
That wraps up today's session. Thanks for tuning into the AIA Research Academy. This academy exists thanks to the generous support of the Gaffasi Foundation and is here to make aromatherapy research fun, accessible, and relevant. Our mission is simple yet powerful: to educate, inspire, and connect a global community committed to advancing the science of aromatherapy. We envision a future where research is not just part of the conversation, but the culture. The best part, access is completely free. Simply sign up through the link in the description box below. And if you're an AIA member, the Academy is already part of your member benefits, putting powerful resources right at your fingertips. If you're passionate about deepening your understanding of aromatherapy through research, you're in the right place. Be sure to subscribe and hit the notification bell to stay connected with our latest sessions. We appreciate your curiosity, your time, and your commitment to learning.